Inverse trig functions, derivatives. Let's derive a formula for finding the derivative of y equals inverse sine of x. If y equals inverse sine of x, then sine of y would have to be equal to x. Taking the derivative of both sides and solving for dy dx, I get dy dx is equal to 1 over cosine y. Now I need to find an expression for 1 over cosine y. To do that, I'm going to look at my right angle trig. Well, I know that sine y equals x, and so opposite my angle y would be x, and on the hypotenuse would be 1. And then what's my third leg? Well, I'm just going to use my Pythagorean theorem to find my third leg. And that allows me to find cosine of y. Once I find cosine of y, I go back to what I was working on. Remember that dy is equal to 1 over cosine y, and I just discovered that 1 over cosine y is 1 over radical 1 minus x squared. And so the derivative of inverse sine is 1 over radical 1 minus x squared. And if I'm using the chain rule, that means I need to go the derivative of what's inside divided by radical 1 minus the square of what's inside. Now, you don't have to, be able to derive this. I just thought you might want to see where these rules come from once in a while. The rest of the video is going to be using these rules. And so we found the derivative of inverse sine, but we could do this for any one of the other 5 inverse trig functions. As I said, let's do an example. Let's just see how do you use these rules. We'll start off with this one. What is the derivative of inverse sine of x squared minus 1? Well, using my rule with u being x squared minus 1, I have x squared minus 1, the derivative of that, divided by radical 1 minus x squared minus 1 quantity squared. Take the derivative, and then I also need to simplify what's underneath the radical. And after I do that, I'm all done. Let's do another example. As the sun descends behind the 150-foot wall of a baseball stadium, the shadow of the wall moves across the field. Let L be the line segment between the edge of the shadow and the sun. Let theta be the angle of elevation of sun, that is, the angle between L and the horizontal. The length of the shadow S is the distance between the edge of the shadow and the base of the wall. Express theta as a function of the shadow length S. I'm going to use tangent. Tangent of theta is 150 opposite, 150 is my opposite, over S, which is my adjacent. So I just went tangent theta equals opposite over adjacent. I could have also done cotangent if I wanted to. After I get that expression of tangent theta equals 150 over S, that tells me that theta is equal to inverse tan of that ratio 150 over S. Let's compute d theta ds for S being 200 feet. Well, I need to remind myself what is the rule for derivative of inverse tan. I need to use that rule combined with the chain rule. So the derivative of inverse tan of u is equal to u prime over 1 plus u squared. And in this particular case, u is equal to 150 divided by s. So do your setup. So we set up the derivative, and then we take the derivative of 150 over s. We also find what is 150 over s. We find out what's the square of that. Now, just to remind you, the derivative of 150 over s, that takes a little bit of work, and I show you here how to do that. After the cleanup, I get 150 over s squared plus 22,500, and then notice the negative in the front. When s is equal to 200 feet, I get negative 0.0024 radians per feet. So the answer makes sense. If the shadow length is increasing, the sun is going down, and so the angle of elevation would be decreasing. And when the length of the shadow is 200 feet, the angle of elevation is changing at a rate of about 0.138 degrees per foot. Take care, and I'll see you in the last section of, the last part of this section. Have a great day.